again, welcome back to the latest lecture session. Again, what have we been looking at? We have been looking at a case study with respect to the application of, or the initial applications of application of PRB, let's say, right? And I think the case we looked at, or were looking at, let's say, was a site contaminated with uranium among other heavy materials, right, or heavy metals, pardon me. And since typically, we give greater weightage to the one that's of greater priority to us, so the relevant people were looking at attenuation of uranium, right? So in that context, as we were aware of, they put in at a field scale or pilot scale, let's say, after relevant laboratory tests, they put in the pilot scale, what do we say, test, let's say, or the emplacement, if I can say so, of three kinds of PRB consisting of different reactive media. I mean, different reactive media in the sense that they chose three different kinds of process: reduction and precipitation, only precipitation and adsorption, right? Different kinds. And then we looked at the relevant aspects. Obviously, we need to look at these aspects to understand, some of the key aspects here that provide greater, or no, not greater, let's say, further knowledge about, evaluating the relevant applicability, let's say, or advantages of each of these materials now, right? So let's move on. I believe we did look at one aspect, but we are going to look at that again because it's relevant to some of the aspects we are going to discuss today. So change in dissolved oxygen concentration. So obviously there might be limitations again with respect to the thresholds for the DO levels downstream, but that's something you need to consider, right? So on the y-axis we have DO, right, and on x-axis we have the relevant date. And we have the three kinds of materials: the phosphate based, zero valent iron based, and amorphous ferric hydroxide based, right? And this was with respect to the, I believe, adsorption was the mechanism. Here I think precipitation, right? And here I believe it was reduction and then precipitation, let's say, right? Anyway, these were the mechanisms that were supposed to be the case. Again, as we looked at it, not a lot of data was presented with respect to validating the mechanism, but again, if you look at the relevant materials, it's logical, and there is historical data to support this particular hypothesis here, right? So moving on, we are trying to look at DO. So DO, what's it now? Oxygen in the aqueous phase, right, in the groundwater. And typically, let's say, how would this be affected? So oxygen, let's say, again, is an electron acceptor, right? So it would be affected, let's say, or the concentrations would be affected when you have relevant reduction or redox process going through, let's say, that would affect that would involve oxygen, right? So obviously in the three of these types of barriers, one of the relevant material is obviously made of a reducing agent, which is zero valent iron, right? So obviously if you look at the data, that particular data pertaining to the zero valent iron based system obviously would have lower DO concentrations. Why is that? Zero valent iron, let's say, is a reducing agent, and even after let's say the first oxidation step to Fe2 plus, pardon me, Fe2 plus is again a reducing agent, and both these particular compounds can react with oxygen, right, which is an electron acceptor. And I think we looked at the relevant reactions earlier. So we have Fe0, which can go to Fe2 plus 2 electrons, and Fe3 plus 1 electron, right? So as you see, a reducing agent or electron donor, and oxygen is an electron acceptor. So right, you can have consumption of oxygen here, right? So that's what you see here with respect to the data pertaining to zero valent iron, relatively low, or below the detection limit anyway, right? So obviously then we see a slight increase, right? A slight increase here, not a great increase, a slight increase. Again, one of the aspects we considered, or we hypothesized, was that you have zero valent iron, and over time you have buildup of relevant precipitate, let's say, on the relevant zero valent iron. So you are going to have what we say, lesser available surface area, or the active sites, and thus let's say the relevant reactions, let's say, or the retention time might decrease, and also the kinetics will be relatively slower in that context, right? So that could be one of the two reasons for this increase in oxygen concentration, among other aspects. Obviously with respect to the other two processes, I believe they follow different what do we say, mechanisms, but typically let's say they would be, if I had the data for the dissolved oxygen concentration of the water coming into the PRB, they would more or less, if not mirror, be similar to that particular profile, and that's what you expect or see out here too, right? Again, moving on. So dissolved oxygen, right, that's something that we looked at, and now we are obviously going to look at oxidation reduction potential, or the redox potential. I mean, a simple way to do that would be to put in a ORP probe, but again, that's not a great way to go about it, but that's what people sometimes typically do. So, but you should be aware that, just relying on this particular piece of data, which is the ORP, measurement, let's say, to understand your system is not a great idea. We'll look at that later, but in this case, let's look at that. So again, oxidation reduction potential is what we are looking at, let's say, right. So obviously, if you have a reducing agent present in that particular solution or that system, what would you expect? You would expect, reducing conditions to prevail, right. So reducing conditions to prevail, so the reduction potential will be relatively less, or ORP reading will be less, oxidation reduction potential. So as expected for zero valent iron, what's the case? It's pretty low, right, and not so the case with the other two materials, let's say PO4 3- and AF, or the phosphate and amorphous ferric oxyhydroxide, let's say, right. So again, if you look at the oxygen profile too, right, in conjunction with this data, you can understand the system obviously, right. In the zero valent iron based system, obviously the oxygen concentration is low, oxygen is an oxidant, right, oxidizing agent, and that's not present, but we have zero valent iron present, which is a reducing agent. So obviously the ORP potential will be lower in that particular case, right. What does that tell you? It tells you that the particular system has reducing conditions prevalent in that, right. So that can be used to understand, let's say, or the other aspects of your system with respect to either uranium reduction or any other compounds in general, let's say, right. So that's something you can look at to understand, right. So let's move on. So here is one key aspect we need to look at. So changes in ferrous iron concentration, right. So obviously we have Fe0 going to Fe2 plus 2 electrons. This is 1/2 reaction, and if it goes to the complete Fe3 plus electron, and typically Fe3 plus is insoluble, okay, it precipitates out typically anyway, right. So let's try to understand this system about what we have here. So what do we have here? On the y-axis we have the ferrous iron concentration in milligram per liter, right. So from 12 to 2, let's say, right. And here we have different monitoring wells in the particular PRB, and what do we have here? Obviously 3 cases. One is when upstream of the PRB, downstream of the PRB, and within the PRB, right. So obviously, upstream of the PRB, let's say, depending upon the groundwater conditions, you are going to obviously expect some ferrous iron present, and that's something that you see here. Depending upon the method detection limit, obviously you can have a variation here. So obviously upstream too, you have some particular ferrous iron. Iron is present in our soil naturally, right. So again, but I guess not at great concentrations or similar concentrations downstream. Let's try to understand this again later. But obviously you see that within the PRB though, the concentrations of ferrous iron are pretty high, right, are pretty high. Let's try to understand this particular system now. Before we go further, let's see that there are 2 rows, primary rows of monitoring wells, row 1 with this suffix 1 here, right, and the second row out here with this one of the suffixes being 2 here, let's see, right. And then obviously one particular system out here, but this is something we are not going to discuss in detail. And keep in mind that when we looked at the particular PRB, and this is the side view, let's say, right, and let's say the groundwater level wasn't, what do we say, uniform throughout the PRB. If you remember that, it had a gradient, a considerable gradient, either this way or this way, right. You had that particular gradient in the groundwater, what do we say, level, right. Again, that's obviously because we were, or the particular site was very near this particular stream, which can act as either drain or recharge for the relevant aquifer, right. Again, that's something to keep in mind. Let's see why that's relevant. So here, as you see, in the ones or monitoring wells pertaining to the first column of monitoring locations, let's say, what do you see? That I guess obviously higher concentrations of ferrous iron in the first set. Let's see what this is. This particular cell is pertaining to ZV1R12, ZV1R12. So this is the first one, as in groundwater flows in this direction, right. And obviously this is the cell that first comes in contact with your particular contaminated water, let's say, right. And obviously you would expect that the relevant concentrations or the relevant and thus the relevant kinetics of the process are going to be faster initially. Why is that? So the rates are dependent upon, let's say, if A plus B goes to products, what do we expect now? What is the rate? Rate equal to the rate constant times concentration of A, concentration of B, right? So if I have my PRB, this is the top view again, similar to the one on the next slide, right? And I have one particular monitoring location here and another location here, and let's say the water is flowing on this direction, let's say, right? So obviously the greater, let's say this is 0 valent iron and this is your contaminant here, right? So at which particular location will you have greater concentration of your contaminant? Obviously out here, right? So you would have obviously greater rates at that particular location, which was or is ZV1 R12, right? So and thus what would you expect? If you look at the stoichiometry and the rates, let's say, you would expect that more of the 0 valent iron would be transformed into ferrous iron, right? So that's something maybe you can look at that or understand that from that point of view, right? That's one particular case. And then obviously as you move further up, or as the groundwater flows through, what do I see though? The relevant kinetics, if not the kinetics, the concentrations of this particular contaminant, right, are going to decrease as I move through the relevant reactor, right? So the kinetics, at this particular case are going to be low, or in the first case there is not just enough contaminant for the relevant reaction to proceed. Even if the kinetics is fast, let's say, and if we consider that to be an irreversible reaction more or less, right? And you still need the relevant contaminant for the redox process to go through. But if most of the contaminant has been degraded in this particular cell though, right, what would that mean? That there is not enough contaminant for the redox process to go through, right? Redox process means transfer of electrons. So here 0 valent iron is your electron donor. So if you don't have an electron acceptor though, right, the redox process will not go through, and that's something that you see. Obviously the case is that we have both the contaminant and oxygen to be our electron acceptors. So that's something that needs to be considered, but obviously we do not have the data for oxygen concentration as we go through the relevant particular PRB, right? But that would be interesting to have that. And here though we see that it's a slightly different profile for the ones in the second column of wells, that the concentration of ferrous iron is pretty high, right? Ferrous iron concentration, the cells are 2, 5 and 8. So I think 2, 5 and 8, right? So this is what we have. And compared to this particular location, the concentrations in these particular locations of ferrous iron are pretty high. Now why is that? So this again we need to go back to the relevant aspects of the site characterization. If you look at that, we saw that the influent concentrations, let's say, were not uniform across the particular PRB, right? So at particular locations they are pretty high, at particular locations they were not. And also we had a gradient with respect to the groundwater table, let's say, right? So it depends upon the amount of contaminant that's actually coming in contact with your relevant PRB, let's say. So looks like more of the contaminant is coming in contact with the relevant PRB in this particular section, or half if I can call that, and thus more of the 0 valent iron is oxidized to Fe2 plus, let's say, right? But lesser of the contaminant is coming in contact with this particular section of the PRB, and thus you have lesser concentrations of Fe2 plus in this location, right? So that's what we see out here. So in this particular cells, let's say, as you can see in these locations, concentrations of Fe2 plus, which would indicate, let's say, reduction, let's say, or the extent of reduction, if I can say that, but if I assume complete reduction, assuming that the kinetics are pretty fast, this would give you an idea about how much contaminant is coming in. And obviously here you see greater concentrations of Fe2 plus, right? So again this comes back to or points at the relevant influent concentrations of uranium coming in contact with these cells. But again keep in mind that there are some loopholes with respect to this hypothesis, as in we know that Fe2 plus can be further oxidized to Fe3 plus and electron given out, and Fe3 plus is insoluble, it will settle out, let's say. So it could as well be the case, but again we do not have as much data at, let's say, or we do not have the historical data either, that Fe2 plus 2 has been further oxidized to Fe3 plus in this particular set of wells, right? Set of wells as in column 1. But typically as when we looked at the site characterization data, or if we look at it in more detail, let's say, we will see that it's because of the variation in concentration, and it's not due to this reason, but it could as well be that this particular aspect of Fe2 plus, whatever Fe2 plus is formed, is again reducing the relevant contaminant and transforming to Fe3 plus. So that's one reason why you could not or might not see this particular concentration in here in this particular column of monitoring wells, right? Again, this is the one in the middle, right? I think that's points to the shift between column 1 locations and column 2 locations, right? And then down gradient, I guess, right? Obviously, depending upon the season, right, you have different concentration of oxygen, which is a competing electron acceptor, and you also have different what we say concentrations coming in. So obviously you see some effects of seasonal variation, but again that's some variation but not a lot, right? So that's something to keep in mind again, right, which is indicative of the reductive process going through, right? How can I be sure that the reductive process is going through? By obviously looking at the byproducts, which are, let's say in this case Fe2 plus, and also oxygen concentrations and ORP potentials and so on, right? So we need to look at the system holistically. And moving on, and for the amorphous ferric oxyhydroxide, so here we have ferrous iron concentration in the y-axis or on the y-axis, and in the x-axis we have the monitoring wells. And again, I believe these are the ones above or up gradient or upstream of the PRB, downstream of the PRB, and within the PRB, right? And I think one again pertains to set of columns, let's say on the left hand side. I think I have the data here again to this particular set of monitoring wells. Again, what is this though? This is the top view of that particular PRB. And what kind of PRB are we talking about here? This is the amorphous ferric hydroxide. Again, the key is that iron here is present as Fe3 plus, right? Amorphous ferric hydroxide, right? Again, as we mentioned, Fe3 plus is relatively insoluble, right? Most of it is present in the, again, the concentrations of Fe3 plus in equilibrium with the solid phase are going to be relatively less. As in, what does that mean? Fe3 plus is typically insoluble, right? Again, this acts as a good adsorbent. So what do we see here though? And again, down gradient. Obviously, the first case is that, this is the lower reporting limit. And the one aspect that needs to be looked at when we try to understand this data is that because we just looked at the data for the zero valent iron based PRB, and what we see there that the concentrations were varying depending upon the relevant situation. So obviously when we try to look at the relative comparison, you need to keep in mind that here the scale is different, as in the maximum here is 1 milligram per liter, and out here we had around this is 12 milligram per liter, so one would be somewhere out here, right? So you need to understand that the axes are different, and thus when you can't make for straightforward or make straightforward relative comparisons, right? So again, what do we see here? So if you look at that, the upgradient wells or the water coming in has some ferrous iron as expected, right? And again, when as the water passes through the system though, is there any source of Fe2 plus coming into play here? Not really. Why? Because you have the Fe3 plus in the solid phase, let's say, which is the amorphous ferric hydroxide or oxyhydroxide in the solid phase, let's see, right? And here, how is the uranium being removed? I believe it's by adsorption onto this particular solid phase, right? You have this amorphous ferric hydroxide. Amorphous is the state, let's say, gives you an idea about the structure more or less, right? As a crystalline, amorphous, and so on. Again, that's something aside though, I digressed. Again, so we have this solid phase material, in which iron is in the form of Fe3 plus and uranium contaminated water flowing through, and we presume that it's adsorption that's occurring. And again, keep in mind that there is no obviously transfer of electrons involved in this place or in this particular context. And even then, let's say for Fe3 to be reduced to Fe3 plus to be reduced to Fe2 plus, you need what do we need now? For Fe3 plus to be reduced to Fe2 plus, you need a reducing agent or an electron donor, and obviously that's missing out here too, right? So obviously what we are trying to hint at is that you would expect no ferrous iron to be formed in this particular or within this particular kind of PRB. Why is that? Because here we have Fe3 plus base system that's acting as an adsorbent here, right? And so that's why you see that the concentrations of Fe2 plus throughout the system, both upstream and downstream and within the PRB are more or less pretty low, right? That's something that we see here. So moving on, and here though for bone char based PRB, right? And I think phosphate was the issue here. right? So we are not looking at ferrous iron here, we are looking at the phosphate concentration and milligram per liter, okay. And keep in mind here that it's not the scale here is logarithmic scale 0.1, 1, 10 and so on, right. So what does that mean? Let's say if I look at this particular case, you know, this more or less means that the concentration here is 10 times what it's here. So that's more or less negligible compared to this particular case, right. So again, what are we looking at? We are looking at the phosphate concentration here, right. Again, the hypothesis was that for this particular kind of PRB material, that, you know, it will have uranyl phosphate, you know, uranium precipitating out in the form of uranyl phosphate and such, right. And that's something we looked at, I believe, the relevant molecular formula and so on, right. So obviously, one of the aspects that we looked at though was that when we were evaluating this material, or when the relevant people were evaluating the material, and we looked at this particular data, we saw that some of this particular bone char material was, you know, leaving this particular system and traveling downstream, right. I think that's something we looked at, as in we looked at the filtered and unfiltered samples, and we saw that with respect to, there was a particular deviation with respect to the relevant what do we say, concentrations, right. Why is that? Because some particular colloids were leaving the system, let's say, right. But obviously again we looked at the data and we saw that these colloids were being again entrapped within the soil. So again, but that's still an issue. So let's try to look at that or understand it in terms of this system. So up gradient within the well and down gradient though, right. And let's look at the data. So initially we have relatively low concentrations of phosphate, pretty low, right, 0.1 to 0.01 milligram per liter. Obviously it varies with season, but something that you would expect, right. But obviously within the PRB, across all the particular, almost all the particular monitoring locations within the PRB, you see that, you know, the phosphate is you know, released, let's say, or, you know, you have phosphate in the particular aqueous phase, right. This is the phosphate obviously in the aqueous phase, and that's something, you know, that hints at the change in phase, let's say, and you see that the concentrations are pretty high or remarkably high, right. And that's something that you need to make sense of in the context of understanding that, you know, these particular what do we say, compounds or the barrier material, pardon me, seem to be mobile, let's say, but typically you want your PRB material to be immobile. So that's something that we need to look at or consider, right. And obviously you can have dissolution of the relevant material of this particular bone char or phosphate based PRB. But as you see though, down gradient the concentrations are not that high though. They are higher or relatively higher maybe compared to the upstream, but down gradient they are not. Again, why is that? The reason lies in that we have colloids being formed, and let's say you have soil, and now these colloids are traveling along with the groundwater after they left the PRB. They are traveling along with the groundwater. But again, you have size, it can be entrapment or adsorption onto the soil. What this shows though is that even though the relevant PRB material has or is mobile and leaving the system, let's say, or has the potential to leave the system, it's not traveling a great distance downstream though. So that's something that we can understand from this data, right. Obviously, you know, water coming in, concentrations of phosphate are relatively low here, right. And then we saw that the concentrations at these wells of phosphate are pretty high, but we see that down gradient though the concentrations are not that high, right. So let's move on here. So obviously until now we looked at the relevant aspects. How did we go about that? Let's just summarize this. We looked at, or they looked at rather, you know, uranium contaminated site among other heavy metals also being present, right. And they looked at the case of conducting, what do we say, field trials. Again, keep in mind that this was, I believe, one of the initial cases for what do we say, field trials, and then full scale emplacement of PRBs. So obviously extensive background work was required. So initially they tried out a lot of materials for batch systems, let's say, and see whether they worked or not. Based on that, they screened them down, let's say, to 3 kinds of process, and then from those process they chose different materials or materials that would, you know, follow those types of process. What were those process? One was precipitation, one was adsorption, one was reduction, and then precipitation, right. So in this context they chose materials and then conducted the column studies, right. Looked at adsorption, desorption, and equilibrium or breakthrough. What's the case? Why is desorption relevant? Let's say if all the uranium is removed, you still have the PRB there, and then the contaminated groundwater, uncontaminated or the pure groundwater comes in contact with this PRB. If the relevant uranium again is desorbed into the groundwater, that's an issue. Obviously, in that context, the relevant data was looked at. We looked at or analyzed that, moved on, and then chose one particular material for these three materials or such, and then we analyzed the relevant data. So as you see, as we looked at, let's say from all these sets of data or humongous amount of information that's available, we see that zero valent iron based PRB, at least for the one that they chose, let's say, was much better in almost all the aspects with respect to reduction and precipitation of uranium, let's say, right. There was no breakthrough, let's say, and the concentration was less or is almost zero or negligible of uranium anyway, right. And again, zero valent iron wasn't mobile or such, yes, that's something that we see or know too, yes. But obviously dissolved concentration is low, but I think that's a balance or trade-off that's acceptable here, right. So obviously we looked at the relevant aspects, but now we are going to look at, let's say, the other important aspect, which is the cost, let's say, which are the costs, right. So initially, let's say, I think the estimate was for around $250,000 or $250,000, right. Again, if we compare that to other process, let's say pump and treat or such, for a year or 2 years, let's say, considering capital cost and such, it will be around 7 million. Million means, I believe, 10 lakhs, right, or 70 lakh US dollars compared to, let's say, $250,000 or $250,000. So you can understand the relative cost here, right. But again, this data is obviously for, let's say, a field scale emplacement, and I'm comparing the data for maybe a full scale pump and treat system. So we can't compare that, we can't have direct comparisons, but you can still understand the degree of what is the difference in the cost, right. So here let's look at the final cost for this particular PRB, and let's see what are the major aspects that increase the relevant cost, let's see. So here we are going to look at the initial phase, right. Obviously project planning and site selection is an issue, yes, and laboratory testing of reactive materials, this was the one for the batch studies or column studies, right. Selection of reactive materials, again from column studies. Regulatory permitting, obviously people need to deal with the relevant regulations and the relevant cases, right. So that's something out here. And site health and safety plan for site characterization, as in to see to it that it's relatively safe for operation. And obviously the major aspect would have been site characterization, cost for understanding or analyzing the particular site or site characterization. So you see that it's around $250,000 or $280,000. And phase 2, we have obviously the design of the PRB, that's something we know how to do, the thickness, so we can get that if we have all the relevant data. Design of obviously the monitoring network and logistical planning, typically monitoring network is key here, right. And analysis and avoiding subcontracts, minor issues with respect to their management, and again development of health and safety plan. Again the cost here though, again because they are mostly office relevant or blue collar type jobs and the relevant work. So you see the costs are relatively less, right, but typically site characterization is relatively costly, and that's what would have contributed to the cost here, right. So again we looked at 2 phases, and obviously the third phase is purchasing, shipment and so on, excavation of trench, maybe not that costly but still adding to the relevant costs, installation, and then placement of the PRB or constructing the PRB, if I can say that, and recontouring operations so that the site isn't affected. That again adds up to about $250,000. So what did we have for phase 1? I think around $280,000, and for phase 2 I think $150,000, right. And you can see how the costs add up, right, to around $6,75,000, but still you see that it's pretty less than what you would consider for any other kinds of treatment systems. But obviously for PRB, the site conditions should be suitable, the type of contaminant and so on. But again in this case we do see that that it's typically economically feasible, and we see what are the major aspects here. Again the costs are cover all the aspects, as in the logistical cost with respect to purchasing, shipment of material and such. Again zero valent iron is relatively cheap, bone char too, and amorphous ferric oxyhydroxide is cheap too. So again these materials are not costly, and again obviously that adds value to your particular project, right. So in conclusion, what can we decide though? We can decide that PRBs are an efficient, right, and more importantly financially viable means, right, of remediating uranium contaminated groundwater or any other groundwater contaminated with, let's say, the relevant type of contaminant. Obviously, in this case, we looked at uranium contaminated groundwater, but obviously it's applicable to different aspects. That's something we looked at in great detail earlier. Yes, and obviously, as we just discussed, it can attenuate other contaminants either by reduction or by even for acid mine drainage. We mentioned that if pH is the issue, we can have a barrier or reactive media that, let's say, acts as a base, let's say, to neutralize that particular acid. That's something else. Even heavy metals, let's say, you can have reduction in precipitation, let's say, right, or you can have a barrier that just increases the pH such that the heavy metals are precipitated out. Yes, that's various applications. And again, keep in mind that this project was one of the initial projects, let's say, and as you can see that they have wide applicability, right. Again, what are the aspects? If we looked at some of the pictures, let's say, structures of subsurface, monitoring is pretty limited, let's say, yes, before, after and at the sites, and then you can get your relevant analysis done, right. So I guess with that, I'm going to wrap up the permeable reactive barrier based aspects, and we are then going to move on to the relevant aspect, which is natural attenuation and also bioremediation within that context in the next session, right. And I guess I'm out of time, and thank you.